Hi, Chem 100 students. This is Dr. Ricardo. We are going to do Chapter 10, which is bonding and the properties of solids and liquids. It's probably the first of 3 videos for Chapter 10. So the first thing we just want to review, we've learned a lot of this already, is we want to review the concept of what's the driving force behind ionic bonding. So an ionic bond is defined as a chemical bond formed by the electrostatic attraction between positive and negative ions. So usually what happens is that you have a transfer of electrons, which is an oxidation reduction reaction, where a metal from the left-hand side of the periodic table donates electrons to a nonmetal and makes an ionic solid at the end. So I have an example, and an ionic solid is defined as a salt. So something like sodium solid plus chlorine gas, making sodium chloride salt is would be defined as an ionic bond. What's holding the Na pluses together with the Cl minuses? Just the electrostatic attraction between the positive metal ions and the negative non-metal ions. So let's take a look at that example. If you recall, we learned the electron configuration of sodium is it has the same electron configuration as neon, which is 1s2, 2s2, 2p6, 3s1. So this last electron is the one that we want to concentrate on. If you look at where sodium is on the periodic table, it is the first member of group 1. Let me just get a quick version of the periodic table for you just to show you that real quick. Okay. So sodium has one valence electron, one electron that's available for bonding because it's just starting its 3s orbital, right? This has a completely filled first main level, a completely filled second group, and then now it's just starting the third main level. So the last electron to go in would be 3s1. Well, this 3s1 electron is very vulnerable. It's not held on to very tightly by sodium, so it can easily be sucked away by chlorine. Which, look at chlorine's situation. Chlorine is atomic number 17. It has the same core electrons as neon. Again, 1s2, 2s2, 2p6. But then, this is number 11, this is number 17, so I have to add, if I got up to 10, I have to add 7 more. So it has a completely filled 3s orbital, and then a partially filled 3p orbital. So it has 5 out of 6 possible electrons, right, to make a grand total of 7. Well, remember, there's a special stability associated with completing a row on the periodic table, right? So this would have its second main quantum level and almost 1 electron from being filled up if I could make this 3p6. So that's what happens. This electron gets transferred. Sodium becomes sodium plus 1, which has the same electron configuration as neon. 11 protons in the nucleus, but only 10 electrons zipping around the outside gives you a gives you a plus 1. And chlorine here takes on 1 extra electron, so it has the same as sodium, 3s2, 3p6, right? So this has 18 electrons, but only 17 protons. So 17 positives and 18 negatives gives you a charge of -1. Okay, well, we're not going to do this for every single chemical reaction. There's a much simpler way to look at it. Okay, so just reviewing for 1 second, this one has 1 valence electron. This one has 7 valence electrons. And valence electrons are electrons in the outermost principal energy level. Everything underneath here has 1s and 2s in the front. Let me just get a post-it and show you that. Okay, if I replace my shorthand notation of what is neon 10, neon 10 is 1s2, 2s2, 2p6. So there's 10 electrons, plus here's the 11th electron. So I can put this right over here, right? Let me just put this back a little bit. All right, so how's that? So how many electrons in this situation are valence electrons? Only 1. Okay, only 1. So this is same as neon 10. So right now I have it written out for sodium. Okay, so sodium 11. One S2, two S2, two P6, three S1. If I have a 1 or a 2 in the front, then they're not valence electrons. Valence electrons are the electrons in the outermost principal energy level. And this number out in front represents what principal energy level you're in. Remember, that's the quantum number n. So this guy only has 1. Well, 1 is so far away from 8 that the easiest way for it to get to 8 is for it to lose this one. And then look, it does have 8 underneath, because now if that 3s is gone, 2s are my highest number. So this one is perfectly happy. So the sodium ion is more stable than the sodium atom. Sodium, when you find it in nature, 99% of the time it's already lost its electron and it's become sodium plus 1. Well, let's take a look at chlorine situation, right? If I was doing chlorine 17, would be, here's my 17 electrons. Chlorine 17, 1s2, 2s2, 2p6, 3s2, 3p5. Count these numbers up at the top, you'll get 17. There's 17 protons in the nucleus of chlorine, that we can't change. Chlorine atoms have 17 electrons. 10 of them they hold on to very tightly. The ones in the first main level are completely filled. Remember, it just takes 2 electrons to fill the first main level. Then this 8, remember that's a magic number, right? We want to try to get to 8 electrons in principal energy levels beyond the first one, right? That's going to be what our goal is, to get to 8. Well, I've got 8 right there, so that's very stable. Now it's got 7 more, right? In its third main level, it's got 2 here plus 5 here makes it 7. So rather than give up all 7 to get to 8, that's crazy. What would it do instead is just capture 1 from something like sodium to become chloride ion, Cl-1, which has 18 electrons zipping around the outside, right? Completely filled first main level. It only takes 2 electrons to fill the first main level. Completely filled second main level. Completely filled third main level. 8 in the second, 8 in the third. The chloride ion is super stable. So there's a huge driving force for this reaction to happen, okay? And it's the fact that sodium's got 1 extra electron and chlorine needs 1. In the end, they'll both wind up with an octet in their outermost principal energy level. So take-home lesson for this chapter, the driving force, what's causing the chemical reactions, is that atoms are trying to have 8 electrons in their outermost principal energy level. Okay, now again, we're just going to do that one time. Now we're going to take a simplified look at this, which is the Lewis picture. In the Lewis picture, all we show are dots around the symbol, and the dots represent how many valence electrons it has. Again, electrons in the outermost principal energy level. Okay? So we just learned that sodium has 1, but there's going to be an easy way to figure that out. Sodium has 1 valence electron because all of the atoms in the first group of the periodic table have 1 valence electron. All of these guys have 2. We're going to skip the transition elements for now because they have varying numbers. Then this column has 3, 4, 5, 6, 7, just like we did with chlorine, right? Because they're 1 electron away from having a completely filled 2p. And then the guys who don't get involved in any chemistry at all, the noble gases, the inert elements, they already have 8 valence electrons. So again, valence electrons are the electrons that are needed for bonding. If you want to count them up, sorry, let me just do a little better. Sorry, that's jumping all over the place. Okay. If you want to count them up, everybody in the first group has 1, everybody in the second group has 2. Don't worry about any of these guys here or any of these guys here. We're not going to work with them. 3, 4, 5, 6, 7, 8. So for the main group elements, the number of electrons that can participate in bonding is what group you are from 1 to 8. Again, 1, 2, 3, 4, 5. How many valence electrons does nitrogen have to participate in bonding? 5. How many does oxygen have? 6. How many does tellurine have? 6. Everyone in this column has 6. Okay, group 16. Then group 17, the halogens, they all have 7. They're 1 away from happiness. 8 is happiness. These guys all have 8 already. Okay, because they have a completely filled up S, and now they're working on their P when they get over here, right? S's and P's, a completely filled up S and a completely filled up P would give you 8 valence electrons. Okay, so sodium we know now has 1. How are we going to arrange these dots? Again, sodium has a total of 11 electrons, but we're only interested in the 11th. The other 10 are core electrons held onto very tightly by sodium. They're not going anywhere, so we're not going to write them over and over again. We're just going to write the symbol and put 1 dot for its 1 valence electron. Here's chlorine with its 7. How should we group them around the symbol? If you have 7, doesn't matter where you put them, but put them in groups of 2, okay? In other words, it doesn't matter that it happens to be on the left side that this guy only has 1. I could have had that over here, over here, over here. Put it wherever it works out for you to make the pictures nice, okay? But if I have 7, I don't want to put all 7 in one place like this. That would be dumb, right? I wouldn't make chlorine and then put 1, 2, 3, 4, 5, 6, 7. They're not all together up there. I put them in groups of 2 because a maximum of 2 electrons can always fit in any orbital. So in a sense, these are kind of like orbitals. So I put 2 on the top, 2 on the right, 2 on the bottom, and since there's only 7, I put the last one on the left. If this would have had 8, I would have put 1 more dot over there. Okay? So group them around the outside. So look how perfect this is. Here comes sodium with its 1 electron that it doesn't care about very much, transfers it to chlorine. Now sodium becomes positive because it donated an electron, and chlorine becomes negative because it accepted an electron. And look at chlorine now. It has 8 valence electrons around the outside. 2, 4, 6, 8. Used to have 7, now it has 8. So this is a very stable structure. How does sodium chloride solid exist? Well, we know that the ionic compounds exist as crystal lattices or crystal structures. There's not really one sodium attached to one chlorine, and they're paired up forever, like they would be when we learn about covalent bonding, like this one is hooked up with this one. It really is that all the sodiums donate electrons to all the chlorines, and then they group together in the lowest energy arrangement. Okay, I'll make this a little bigger. The lowest energy arrangement is that each sodium is surrounded by chlorine. So you can't see it, but there's a negative sign in the middle of each of these. So their nearest neighbors are the opposite guys. Why? Because opposites attract. And then the next sodium would be over here, which is further away, right? Because like charges repel each other. And where would the next chlorine be? Here and here. So if you think about a flat floor, in each of the corners of a rectangle, you put one of the ions, make it the negative, and then right in the middle of a floor tile, you'd put the positive. And then that pattern would just repeat over and over and over again. Okay, so if I wanted to do this in 2 dimensions, these could be all the negatives, right, at the corners of the floor tiles. Put my sodium in the middle, then the pattern would repeat in both directions. Positives here, negatives at each of the corners. Okay, positive here, negative at each of the corner. So it's not this sodium with this chlorine or this sodium with this chlorine. It's just arrays of opposites attract. The negatives, you can think of them in the corners, and the positives, you can think of them in the middle. I know it doesn't look like it in 2 dimensions, but there's actually an equal number of both. Well, ionic salts are not in 2 dimensions, they're in 3 dimensions. So stack up another layer of ions on top of this, and another layer on top of that, and another layer on top of that, and you get the real picture, which is in 3 dimensions. So this pattern in the next thing would be a negative would be right on top of the positive because those would be nearest neighbors. And then in the next layer on top, I'd have positives in the corner. And those boxes would just alternate every other one. In the end, I'd have an equal number of sodium ions and an equal number of chlorine ions. So I would say, hey, since it's a 1-to-1 ratio of sodium to chlorine, the chemical formula, the empirical formula, the simplest whole number ratio is just NaCl. Okay? But again, I don't actually have molecules like I'm going to teach you in a little while. I don't have this. I don't have these two guys are together, married forever. I just have arrays of ions. Okay? So that's what the unit cell or the crystal structure looks like for sodium chloride. Okay? Here's another example. The second example is what would happen when magnesium and fluoride are put together. Well, the magnesium has, this guy's not there. Okay, so the magnesium has 2 valence electrons. Why? Because magnesium is in the second group of the periodic table right next to sodium. So it's a metal with 2 valence electrons. Remember, everybody in the first group has 1, everybody in the second group has 2 electrons available for bonding. Well, 2 is so far away from 8, right? It's not going to grab 6, take 6 from something else. It's much more likely, like sodium, to be an electron donor, to become oxidized, to lose electrons. That's what metals do. So here's a magnesium. A magnesium would get together with 2 fluorines. Fluorine is in group 17, right on top of chlorine. So its tendency is to have 7 valence electrons and get involved in 1 bond to make 8, right? These guys have, remember, look at the whole periodic table. 1, 2, 3, 4, 5, 6, 7. Everyone in this group has 7 valence electrons. These guys have 8. So if it has 7, there it is with 7. Okay. Now, look, I could do this suggestively. I could put 1 on one side and 1 on the other side, and you can see, why would magnesium get together with 2 fluorines, Bill? 1 valence electron would go over to this guy to make him have an octet and a -1 charge. The other valence electron would go over to the other side to make him have a beautiful octet of 8 valence electrons around the outside and a negative charge. And what happens to sodium if it donates 2, not to the same place, 1 to each? It becomes +2 if I give up 2. Now, it's got a valence, a number of valence electrons that's also 8, because if I strip away its 3s1 and 3s2, what's behind it? 2s2, 2p6, so it still has 8. So here's the salt, magnesium fluoride. All the atoms have gained an octet due to the transfer of electrons. 8, 8, and 8, very stable chemical compound. Okay, so in my array this time of ions, remember, an ionic salt is just an array of ions. They would be packed together in an arrangement that, what's going on? There would be twice as many fluorides as magnesiums. So unlike this one, where it was kind of a 1-to-1 ratio, they would just have to be packed together in a crystal structure. I'm not going to show it to you, but a crystal structure in which there were twice as many fluorides as magnesiums. You don't draw individual molecules, though. Okay, we're going to draw the individual molecules for the covalently bonded compound. Okay, here's the last example, I believe. Well, actually, I have 2 more. Okay, here's what would happen when aluminum gets together with oxygen. Aluminum has 3 valence electrons. Why? Go to the periodic table. Here's aluminum. 1, 2. We don't worry about these guys. Everybody in this group here, group 13, has 3 electrons available for bonding. So here's its 3, right? Oops, sorry, get rid of that. here's another aluminum with 3. So I've got 2 aluminums with 3. How many oxygens would it get together with? Well, let's take a look at oxygen. Oxygen is in group 16. It needs 2 electrons to get to 8. So if I have one thing that wants to donate 3 and the other thing that needs 2 to get to 8, how's that going to happen? Now, here's the first interesting thing. Let me make this a little bigger. Okay. Okay, make my dots a little stronger. Good. All right. Here's oxygen with its 6 valence electrons. Put the first 2 together because those represent the 2s, then spread the rest out. So don't put these 2 paired together. First 2 together, you can do that on the top, then spread the rest out. So if it has 6, 1, 2, 3, 4, 5, 6. So if I put the first two together, then I would put my third one here, fourth one here, fifth one here, and then only go back and double up when I have to. Okay. So there's my 6. These two guys are dying for a partner, right? These two guys are already set. There's a special name for that we'll talk about in a little bit. There's oxygen with 6. Here's another oxygen with 6. This time I did the top one and the side one as the ones that are looking for bonding. And the bottom ones and the right ones are set. Here, again, I did the top one and the right one. All right, so you ready? These guys are going to donate those. So let's put one over here, one over here. Now this guy has 3, so he can donate one to the middle. This one is going to come down here. This one's going to come down here to take care of him, and he's got 1 extra to go to the middle. So it doesn't matter actually how you draw the arrows, but 2 electrons from here are going to satisfy this guy to get it from 6 to 8. That leaves 1 to go to the middle guy. 2 electrons from here are going to go down here to get this guy from 6 to 8. Okay, a little hard for you to see, sorry about that. There's supposed to be 6 here. Good, all right. And so 2 will go down here, and that leaves 1 here and 1 here. So what do I wind up with? 2 perfectly happy aluminums, each with a +3, and 3 oxygens, each with a -2. We know those guys are called oxide. And those oxides, every oxygen has an octet. There's its beautiful 8 electrons around it. Aluminums also have an octet. It's number 13. If it gives up 3, it's still got a perfectly good 10 electrons back behind there. Okay, we don't draw it for the metal. We don't put all the electrons because we ripped off 3 because it used to have 3 extra, but now it's got a totally filled 2s and a totally filled 2p. So 2p2, 2s2, 2p6 to make a total of 8. 8 valence electrons give each of these 2 aluminums an octet. Very stable compound. And that would be aluminum oxide. And we would just write it like this, like you already knew. Crisscrossing the +3 and the -2, 2 to 3. So that's how the salts get that way if you want to look at how the electrons are transferred. Okay, let's predict the formulas of some more ionic compounds. Here's magnesium, here's oxygen. Magnesium has 2 to donate. Oxygen needs 2, so the 2 would go 1 here and 1 here. Magnesium would be perfectly happy with an octet, and so would oxygen. Okay, and we knew that already just from our crisscrossing. Here's some more quick examples before we go on to the new stuff. Formulas of compounds formed by the alkali metals. Okay, so the alkali metals are all in group 1. There they are. Right? Lithium, sodium, potassium, rubidium, cesium, francium. All of these have 1 valence electron, so we draw them with 1 dot. All right, if it's going to get together with oxygen that needs 2 electrons, you're going to need 2 lithiums to satisfy 1 oxygen. So the formulas are going to come out to be Li2O. If it's going to get, why? Because these guys have 6 valence electrons. And you already knew this from crisscrossing. Okay? When it gets together with chlorides, chlorides tend to become -1 because they have 7 valence electrons, and you want to get to 8. So if I donate 1 electron, I need 1 of the metal, and remember these guys have 7, so they're only going to get together in a 1-to-1 ratio. 1 of these with 1 of those. And if it's going to get together with sulfates, sulfates have -2, right? That's the polyatomic ion, SO4 -2. So how many lithiums are going to be needed to accommodate it? You're going to need 2 lithiums because lithium loves to become +1. So nothing new here. We knew all this stuff from crisscrossing. Here's another 2 examples. What happens if lithium gets together with phosphorus? Here's lithium with phosphorus. We know lithium has 1 valence electron. Here it is. Everybody here has 1. How much does phosphorus have? Just like nitrogen, it has 5, right? 1, 2, 3, 4. Everybody here has 5 electrons available for bonding. Sorry, I just lost my screen. So If I have 5, how many do I need? I need to accept 3 of them to get to 8, right? 8's the magic number for every element other than hydrogen and helium. Everybody else is shooting for 8. Why are hydrogen and helium shooting for less? Because they're in the first group of the periodic table, the first row of the periodic table, so they're only shooting for 2. There's no such thing as a 1p orbital, so they can't fill that up. So hydrogen and helium are trying to get 2 valence electrons, but the rest of the periodic table is going for 8. Okay, so lithium's got 1 extra. Phosphorus needs 3, so it's going to take 3 lithiums. Each lithium donates 1 to become +1. Phosphorus becomes -3. How about calcium and sulfur? Sulfur is right underneath oxygen on the periodic table, so it has 6 valence electrons. Calcium is right underneath magnesium, so it has 2. So if I have 2 extra and you have 6 and you're trying to get to 8, I can just donate both of mine to you. I can become calcium +2, and you can become sulfide -2. All right, so that's the end of the ionic bonding, which is kind of a review of what we already learned about bonding. So here's the brand new stuff, the idea of sharing electrons or covalent bonds. So I'll describe a covalent bond for the simplest element overall, which is hydrogen, and then we'll talk about who would be interested, which types of elements would be more likely to get involved in covalent bonds rather than ionic bonds. Okay, so covalent bond is a chemical bond formed by the sharing of a pair of electrons between atoms. So when we draw them, we are always going to be working in groups of 2. You can think about 1 electron coming from one of the atoms and another electron coming from the other atom. They're both kind of unstable. They would rather make a pair, so they get together like this, where they share that pair of electrons. So you can draw it that way. Or you can draw them next to each other if you want. That's perfectly good. So that would be sharing a pair of electrons. And the last thing that we can do to abbreviate is anytime we have a pair of electrons that are shared, we don't have to make 2 dots. We can replace that with a line. A line in chemistry represents a pair of electrons that's shared. Okay? One of them is spin up, one of them is spin down. They're not an atomic orbital, they're not a region of space on an atom, they're a molecular orbital. They're a region of space that holds electrons, and it's shared between these 2 atoms. So this, and this all represent a single covalent bond, sharing of a pair of electrons. Okay, let's take a look at the motivation. Why do we find hydrogen in nature always as H2? Well, here's why. Hydrogen is a nonmetal in this case, right? When you put it with another nonmetal, so there's nothing for it to donate electrons to. I have an atmosphere where there's only other hydrogen atoms around. So nonmetals get together with other nonmetals, always in covalent bonding, to make molecular compounds sharing. So we usually think about hydrogen loving to donate its 1 electron, and that's what it would do if there was something else around that needed electrons more. But if the only other thing around is other hydrogen, he has 1 to donate, he's got 1 to donate. Well, why would this one give it to this one, or this one give it to that one? They both are trying for a 2-tet. The better way to get a 2-tet would be, rather than me donate 1 to you so that you get 2 and I have none, why don't we share them? So we can think about this as the 1s orbital on the first hydrogen atom, and we know in our 1s orbital, right, we've got the nucleus. Hydrogen is a super simple atom, right? Hydrogen has 1 proton, no neutrons, right? 1 minus 1 is 0, and it also has 1 electron zipping around the outside. And that 1 electron you could think about as spin up, zipping around in this spherical orbital. We know s orbitals are spheres. Okay, the other hydrogen, same exact situation, but this time you can think of this guy as spin down. So they're perfectly aligned. The spin up one is going to get together with the spin down one. As these 2 atoms approach one another, they attract to one another, not because opposites attract, because they have a mutual desire to have 2 electrons in their outermost shell. Not 1 each, not dot each, right? Why did I make 1 dot for hydrogen? first group of the periodic table. These guys always have one dot. All right, so now they get together, and what would happen if two spheres overlapped? Well, it would make something that looks like a peanut, right? Where the shared space in between, which is where most of the time those two electrons would live, in that space in between, but they could kind of sometimes come and hook around this outside here, right? That's really what the bond looks like. It's a region of overlap, but we can't draw this peanut every time. So we're just going to say that the shared space, now these guys are not dots, these are the nuclei, right? That's the two protons. Okay, so you can think about them as having a +1 inside. So when they get together, they're going to get together and get close to one another and share this space in between. So a region of space that has electron density is a single bond. And I could think about it as one spin up and one spin down. It's a molecular orbital. So what did I have? I had two individual atomic orbitals, this one and this one, overlap, get together to make a molecular orbital. Okay, so this is our first example in the whole course of sharing. And one more abbreviation, instead of writing H dot dot H, I could just write H line H. And that's what H2 is in the environment. We think of H2 gas, it really is a hydrogen single bound to another hydrogen. And those are actually the only two electrons the whole thing has, right? And they prefer to share them because then they can both get two, right? This guy's got two, has two around him, and this guy has two around him. They share the two. Okay, so that's the first example. All right, let's take a look at another example. What would be the driving force for hydrogen and chlorine to get together? So these are going to be called Lewis electron dot structures of molecules. Well, here comes my hydrogen with its one valence electron, and it's in an environment where there's also chlorine around. Well, the hydrogen wouldn't react with another hydrogen because there's a much bigger driving force. The bigger driving force is chlorine. It's got 7 valence electrons, like everyone in group 17. These guys all have 7, right? 5, 6, oh, excuse me, yeah, 3, 4, 5, 6, 7 valence electrons. Totally happy already. Don't get involved in any chemistry with 8. They're done, right? They're happy with 8, right? So you can make a little happy face up there. So they're going to want to bond to collect one more electron or share once. Okay. So here's my hydrogen. Its driving force, hydrogen and helium are in the very first group of the periodic table. Its driving force is to get to a 2-tet. 2-tet would be to have 2 valence electrons around the outside of it. Right now it's only got 1. All right, here's chlorine. It's got 7, 2, 4, 6 that are already paired up, and this one that's all by itself looking for a partner. So what's going to happen is this guy's not going to donate to him. They're going to overlap. The H plus is going to come in contact with the chlorine, and they're going to share space in between. Now, you can take this dot, and those are those 2 dots. Okay, so that's what hydrogen chloride looks like in the gas phase. That's what hydrochloric acid looks like aqueous. It's a hydrogen with 1 pair of electrons shared between it and chlorine. And then chlorine also has 3 other pairs of electrons that it owns all by itself. So these are given different names. The ones that you own by yourself, that you're not sharing with anybody, are called non-bonding pairs because they're not in bonds. Okay? They're owned by the chlorine. Chlorine came in with them. Look, 1, 2, 3. Those 6 dots, 2, 4, 6, are 3 pairs that it owns all by itself. The other one, though, is different. Look, it's in a shared space between hydrogen and chlorine. It's that guy overlapping with that guy. So how would I write that? In an abbreviated fashion? You're going to write H line Cl, and you need these other electrons. Those lone pairs are going to be important for other things. That's the perfect Lewis electron structure for HCl. Let's see if everyone is satisfied. The hydrogen on the left side is satisfied because hydrogen and helium are only shooting for 2 because they're in the first row of the periodic table. So here's my 2. When I ask myself, how many electrons does hydrogen have around it? it has 2 because each line means 2 electrons. It's okay to count both of them, right? When you share something, you kind of say, oh, it's mine, right? And then here's chlorine situation. How many total electrons does it have around it? Surrounding it? It's totally satisfied with 8. 2, 4, 6 that it owns by itself, and 2 that it's sharing with hydrogen, but it's still 8. It's so cool. You're allowed to double count. Any of the shared pairs get counted for both sides. Okay? So happy with 8 valence electrons, happy with 2 valence electrons, right? So hydrogen and helium shooting for 2. All the other elements are shooting for 8. If I'm overlapping chlorine and oxygen and I'm trying to figure out the structure, I'm trying to arrange them in a way that everybody gets 8. 8, 8, 8, 8, 8, 8, 8. We're obsessed with 8, right? Having a 8. Okay, so that's a great example. Everybody's got 8. All right, so bonding pairs are electron pairs that are shared between 2 atoms. Lone pairs are electron pairs that remain on one atom and are not shared. They come in with that particular atom. Okay, first we just talked about all of our examples so far were single bonds. Maybe in order to get to 8, okay, elements might have to share more than one pair. So here's a single bond. It's just 1 pair of electrons that are shared. Here's a double bond. It's 4 total electrons, but you shouldn't think about it as 4 things in a little box. You should think about it as 2 sets of 2, right? Here's the first set of 2. Here's the second set of 2. So there are 4 electrons being shared in 2 bonds. Every line represents 2 electrons. And the highest bond order you can have under ordinary circumstances are triple bonds. There's no home runs. We have singles, doubles, and triples. Triple bond is when 3 pairs of electrons are being shared. So here's 1 pair, here's 2 pairs, here's 3 pairs. And you're going to say, how could that happen? Don't I have just 1 region of space between the atoms? How do I get 3 bonds into 1 space? Well, what happens is the first pair goes exactly where you'd think, in the space between the atoms. The second one shares the space on top and below the atoms, and the third one shares the space on the inside and outside of the atoms. So this could be 1, 2, and 3, and that's how you get 3. So you take advantage of all 3 dimensions, right? This would be X, this would be Y, up and down, and in and out would be Z. So that's 3 dimensions of space. The most you can have is a triple bond. How about if you have 2? Well, if you have 2, the first obvious space, always take advantage of the space in between the atoms. So that could be X. And then the next set, okay, is take advantage. This is just 1 bond, right? This is the space above and below the atoms. So this would be the second bond. And if I just have 1, well, then I just take advantage of the space between the atoms. Okay? So that's what's actually happening, and you'll see that later on. Okay? But for you, for right now, you see 3 sets of electrons. Think about that as a triple bond. 3 pairs of electrons being shared between 2 atoms. Okay, if we want to quantify how strong the bonds are, we can talk about something that you can do experimentally, and that is measure the homolytic bond dissociation energy. So to break a bond homolytically is to break it right down the middle. So the homolytic bond dissociation energy is the amount of energy required to break a chemical bond right down the middle. That means 1 electron goes to the guy on the left, the other electron goes to the guy on the right. So EB is the energy to break the bond. These are all going to be endothermic. It always takes energy to rip things apart, and they break evenly. Okay, so let's look at some examples, and then we'll try to rationalize why the numbers are what they are. So we're expecting all positive numbers, right? This is how much energy it takes you have to put in from the outside to break these chemical bonds. And the bigger the number, the stronger the bonding must be. Okay, so these are examples of diatomic elements, okay, the bonding that occurs inside diatomic elements. So the bonding in homogeneous diatomic elements. So the first one we already did was hydrogen, right? The motivation, hydrogen each has one valence electron. They hook up, they make a single bond, and hydrogen's bond energy turns out to be 436 kilojoules per mole. Okay? So that's on this scale, that's kind of somewhere in the middle, but it's certainly a lot less than the next one and a lot less than this other one over here. So it's pretty high, okay? But much less than this nitrogen-nitrogen bond. So what's happening with nitrogen? So let me show you where nitrogen is on the periodic table. Here it is. Nitrogen is in the 5th column over, right? Group 15, okay? Everybody's got 1, everybody's got 2. We don't do these guys. 3, 4, 5. So there are 5 electrons available for bonding, okay? We'll talk about later on why I'm going to tell you put the first 2 together. You got 4 spaces. You got the top, the bottom, the left, and the right. Put the first 2 together and spread the rest out, and I'll explain that later, okay? So if I put the first 2 together, that gives me 2, and I have to make 5. 3, 4, 5. Same thing for the other nitrogen, okay? Put the first 2 together, 3, 4, 5. Now, there's no correct answer as to which side it's on, okay? But I did it like this because I want to do something suggestively. I want to show you who's going to get together, okay? So remember, atoms can all move around. So this thing could just turn around and look exactly like that one, okay? But if I draw them this way, look, this guy and this guy are going to hook up and make the single bond in the space between the atoms. This guy and this guy might hook up and make the second bond above and below the atoms. And the last set, this guy and this guy might hook up to occupy the space on the inside of the paper and back behind the paper. So that's where the 3 bonds are. So something that only has 5 needs to make a triple bond because I have to get to 8. And 5 plus 3 is 8, right? So now come over here and ask yourself, before they bonded, how many valence electrons did nitrogen have? The answer is 5 and 5. Well, that stinks. Everybody's shooting for 8. How do I get to 8 when I have 5? Bond 3 times. After they bond 3 times, this lone pair here is still maintained. And this lone pair here is still maintained. That's that guy and that guy. They didn't participate in the bonding. It's only the free electrons, the electrons that don't have a partner, that participate in bonding. Okay? All right, so here we go. Ask yourself this question now. Are both of these nitrogens satisfied? Do they have an octet? Well, this nitrogen on the left, lefty, has 2 electrons that it owns by itself and 3 that it's sharing. So even though it's sharing them, I get to count them. I get to count everything that's shared. If I share a car with my brothers and sisters and I go out to a party and people say, "Where's your car?" You say, "Oh, it's right there." You pretend it's your car. You don't say, "That's my car that I have with my brothers and sisters," or "That's my dad's car." You say, "That's my car." So you're sharing it. So for the time that you're using it, it's your car. Okay, you don't have to give everybody the details of who owns the car and whose name is on the title, right? So it's your car. So those 3 that are shared, how many does nitrogen have? 2, 4, 6, 8. How cool is that? He's got an octet. Very stable stuff. 2, 4, 6 that is sharing, plus 2 more that he owns by himself. Okay, cover the other guy up. How many does he have? He's got 2 that he owns by itself, plus 3 sets that he shares. So 2, 4, 6, 8. Both atoms are totally happy. Nitrogen makes up 80% of the atmosphere. It is an enormously stable molecule. It does not want to react with anything. Okay, in Washington, the Declaration of Independence is inside a glass box and it's surrounded by nitrogen. They pump out all the oxygen and only put nitrogen in there, and they constantly supply it with a little bit of positive pressure of nitrogen so that the paper doesn't oxidize any further and yellow any more than it already did. Okay, because nitrogen is very unreactive in the atmosphere. And why? Because it takes a lot of energy to break that triple bond. 948 kilojoules for each mole to break that bond. Good luck with that. Okay, let's talk about oxygen. Oxygen does have a relatively strong bond, but Still turns out that oxygen is going to be reactive for different reasons. But oxygen on the periodic table has 6 valence electrons because it's in group 16, right? Everybody's got 1, everybody's got 2, 3, 4, 5, 6. All these guys have 6. So if I have 6, I need to bond twice to get to 8. Okay, put the first 2 together. I've got to draw my oxygen with its 6. Put the first 2 together over here. Then I go 3, 4, 5. Now, remember, you only have top, bottom, left, right. If I have 6, I got to put the 6th one. He's got to have a partner. So 2 together, 3, 4, 5, then come around and put 6. And look how suggestive that is. Now it's got 2 lone pairs that are it's going to hold on to dearly, and then 2 that are ready to react. This guy's going to react, and this guy's going to react. It's the dots by themselves that are the reactive ones. Other oxygen, same situation. It's got 6. Put the first 2 together. 3, 4, 5. Now I have no choice but to put my 6th one and double it up. Here, I put the first 2 together, and since I only got to 5, I put 1 in each spot. Remember, we only have top, bottom, left, right. Okay, watch what happens. These guys are going to get together in the space right between the atoms. These guys are going to get together in the space above and beyond, below the atoms. And that's it. Each oxygen is going to wind up bonding twice and having 2 lone pairs. Here they bonded 3 times with 1 lone pair each. Okay, let's ask ourselves, are the 2 oxygen atoms happy? Cover this one up. How about this guy Lefty? He's got 2, 4 that he owns by itself, and 2 sets of 2 that are in bond. So 2, 4, 6, 8. The guy on the left is happy with 8 valence electrons. Cover him up. How about the guy on the right? 2, 4 that he owns by itself, and 2 sets of 2 that he shares. So 2, 4, 6, 8. Count every set of dots as 2, obviously, and each line as 2. Both atoms in oxygen have an octet, okay? Yet oxygen is reactive. That's because oxygen has a huge driving force to react and make its way to oxide, whereas nitrogen doesn't have that driving force in ionic chemistry. So oxygen is great at oxidizing metals because it would prefer to be O minus 2. So this can break apart, and I replace it with 8 electrons around each oxygen in oxide, which is even more stable. This is a very stable. That's oxide, right? And we use oxide. It's an ionic species, and it's the substance that you wind up with after something rusts or oxidizes. Okay, let's take a look at chlorine. Chlorine, bromine, and iodine, guys, are all in the same situation, so I'll do those as a group. Where are they on the periodic table? They're in group 17. Group 17, second to last group, right before the ones that already have 8, they have 7 valence electrons. If you have 7, you want to get to 8, you just need to bond once. So draw the 7 valence electrons around each atom and then hook up the ones in the middle. Put the first 2 together. 3, 4, 5, 6, 7. See, I have to double them up because I have 7. But that leaves this one alone. Same thing over here. Put the first 2 together. 2. Then 3, 4, 5, 6, 7. This guy and this guy don't have a partner. Those are the 2 that would share. And here's chlorine. Chlorine gas has a single bond between 2 chlorine atoms. Okay? And each chlorine also has 3 lone pairs of electrons. That guy's happy with 8. 2, 4, 6, 8. That guy's happy with 8. 2, 4, 6, 8. Okay. Leave this one out of the scenario. Leave hydrogen out of the scenario. Just look at these 3 things. They're very close on the periodic table, right? This one, nitrogen, oxygen, and chlorine are almost the same place on the periodic table. And we're looking at the bonding of oxygen with oxygen, fluorine with fluorine, and nitrogen with nitrogen. It's going to turn out that the nitrogens are going to be the strongest bonds because they're going to make triples because they are 3 away from 8. Oxygens are going to be the second strongest because they're going to make doubles. And chlorine and fluorine are going to be the least because they make single bonds. Okay? So triples are stronger than doubles, are stronger than singles. Makes sense, right? So you compare those two. This guy's a little bit of an exception, so let's leave that one out, right? Single bonds, weaker than double bonds, weaker than triple bonds. So that's a general trend. Okay. All right. Leave this one out because it has a little bit of a weird thing going on. What happens if I compare elements, okay? These three down here, and just everything else is the same about them. They come from the same part of the periodic table, but they all have single bonds. But which ones are going to be the strongest? Well, turns out chlorine is stronger than bromine, is stronger than iodine. So the smaller molecules have the stronger bonds, right? The smaller ones have the stronger bonds. Well, actually, that still works in this case, okay? The smaller they are, oops, take that back, right? The smaller they are, the stronger they are, okay? So what's the example, what's the explanation for that? Well, when you go to break apart something that's very large, think about two basketballs that are glued together. It's very diffuse. There's a lot of space between them. So it's easier to pull apart two big things. The sharing isn't as critical. The bond isn't as intense, isn't as concentrated in one place. So if you were asked to compare what is the bond strengths of these three molecules, right, that have a lot in common, they're all coming from group 17, the smallest ones are going to be the strongest ones, right? All just single bonds. These are smaller though, okay? So from the periodic table, bond strength, everything else being the same, these are all single bonds, right? All single bonding species. Bond strength would be greatest for chlorine compared to bromine compared to iodine, okay? Cl2 bonds are stronger than Br2 bonds, are stronger than I2 bonds, okay? O2 are stronger than S2. N2 are stronger than P2. Chlorine, carbon single bonds to other carbons are stronger than silica to silica, okay? Bromine bonds would be stronger than aluminum. The smaller the molecule, the stronger the bonds when everything else is held constant. Okay, here's that trend down at the bottom. So bond energy goes, triple bonds are stronger than double bonds, is stronger than single bonds. And the second trend that we learned, maybe you can cover this up. Second trend that we learned is the bond energy goes down as you go down a group. Okay, last set of notes for this section is what happens, we've been doing examples where both electrons are coming from the same, one electron is coming from each of two atoms. Okay, what happens if one atom has extra electrons that it can provide and the other one doesn't have any? Well, that's called a coordinate covalent bond. It's a bond formed when both electrons of the bond are donated by the same atom. So here's a classic example. Here's the hydrogen ion that makes things acidic. It's actually just a naked proton in solution, right? Because hydrogen is H11 ordinarily. That has one proton, 0 neutrons, because 1 minus 1, and 1 electron. Well, if I take away its only electron and I make H11 plus 1, then the hydrogen ion then is just 1 proton, 1 minus 1 is 0 neutrons. And if I have a plus 1, the only way to get a plus 1 with 1 proton is to have no electrons. So this is just a proton, okay? It has an empty 1s orbital around the outside, okay? But that 1s orbital that's empty can overlap with this beautiful lone pair on ammonia. So this is the way ammonia reacts. Ammonia is already a relatively stable compound. Ammonia is usually found in the gas phase. When it dissolves in water, like you think of in cleaning things like Mr. Clean, not Mr. Clean, Windex, right, is ammonia as the active ingredient. It actually goes into the ammonium ions in solution. But in the gas phase, when you smell things that smell like ammonia, this is what you're smelling. Okay, so let's take a look at it first. Here's the nitrogen. It's got 3 bonds to 3 different hydrogens, right? Because hydrogen is shooting for 2. So this hydrogen is perfectly happy with 2. This guy's happy with 2. This guy's happy with 2. So the hydrogens are all satisfied. And the ammonia is satisfied. Check it out. It's got 8 valence electrons, 2 that it owns by itself, plus 3 that it's sharing, 3 pairs that it's sharing. So 2, 4, 6, 8. So it's pretty happy. But it's generous. It's got this 2 electrons here that if it overlaps with the hydrogen ion, which has an empty orbital, it can make a single bond to a 4th hydrogen. Now, if something positive gets together with something neutral, you have conservation of charge. +1 and 0 have to add up to +1. So this is the ammonium ion that you guys have memorized, NH4+, right? It's your only positively charged polyatomic ion you had to memorize. That's what it looks like. And the cool thing is, once this guy goes on, I can't tell it apart from the other 3. They would all have the same energy. So if it broke apart and went back to ammonia and H+1, there would be an equal probability of any one of the 4 popping off. It wouldn't be, hey, you're the last guy to come in. We were here first, so you have to get out first. Chemistry doesn't work that way, right? It would have an equal energy to the other 4. Everyone still has an octet in this formula, but you've also given hydrogen, this hydrogen over here, you've given it a 2-tet. Look, it's happy with 2 electrons. Here, poor guy had none, right? This is really starved of electrons. So happy with 2 electrons, happy with 2, happy with 2, happy with 2. And what about our nitrogen? 2, 4, 6, 8, happy with 8. So nitrogen did not lose anything. Here it had an octet, here it has an octet. So what's the difference? This is an octet made by 4 sets of bonding electrons, 2, 4, 6, 8. Here's an octet made by a lone pair and 3 sets of bonding, 2, 4, 6, 8. Very cool. Okay, last example. Draw the Lewis electron diagram for BH3 and NH3. Will these 2 molecules react to form a coordinate covalent bond? Okay, so let's put together boron and hydrogen in BH3. So we know hydrogen has 1 valence electron. We know boron has 3. Why? It is in the 3rd group of the periodic table when I skip the transition elements. All these have 1 valence, 2 valence, 3 valence. It's only valence electrons. Of boron's total of 5 electrons, only 3 of them can participate in bonding. The other 2 are held very closely in the nucleus. They are in the 1s orbital. All right? The ones that count are going to be in the 2nd group. So 3 electrons to participate. So there's boron with its 3. Okay, get in good habits. Put the first 2 together, spread the 3rd one out. Okay? This is going to just be temporarily. In a second, this guy's going to rearrange so that it has 3 separate ones. But I want you to get in the habit of always, whenever ask yourself how many valence electrons it has, put the first 2 together, then spread them out. Okay, so there it is, and then I have hydrogen. So you can see what's going to happen. 1 is going to overlap with 1 for hydrogen. The second one's going to overlap with the second hydrogen, and the third one's going to overlap with the third one. And that's how I make BH3, boron trihydride. That's the best I can do. I only have 6 total electrons to work with, so there's no way to get an octet around boron. So this would be a very, very reactive compound, boron trihydride. I'd have to keep it away from water. I'd have to keep it away from anything because it would love to gain 2 electrons to get to 8. Check that boron out. It's only got 2, 4, 6. There's nothing in this space up here. It's dying to react with something to give it 8, and that's what's going to happen. So it's kind of looking for a partner, right? It's got an empty orbital here, all right? Nitrogen, we saw before, has 5 valence electrons, so you put the first 2 together, 2, 3, 4, 5. When it gets together with 3 hydrogens to make ammonia, one of them's going to overlap. This one's going to overlap with the second hydrogen. This one's going to overlap with the third hydrogen. So I just turn this around. Here's the single bonds to 3 hydrogens. We saw that before. Same thing as up here. Single bonds to 3 hydrogens plus the lone pair. So look at these 2 things get together. This is like 2 rocket ships docking in outer space. This guy's got the 2 electrons. This guy's dying for 2. When they get together, they're going to form a coordinate covalent bond. Not one dot over here and one dot over here. That's a traditional covalent bond. A coordinate covalent bond is when both of them come from the same place. They're both going to come from nitrogen. So this two are going to overlap with this emptiness and make a single bond. Now, everybody's got an octet. This had no charge, this has no charge, so the product has no charge. And everybody's got either a 2-tet for hydrogen or an octet for boron and nitrogen. So let's check each hydrogen. Happy with 2, right? Guy on the top, happy with 2, happy with 2, happy with 2, happy with 2, happy with 2. All of the hydrogens are happy just making a single bond. In fact, in all this whole chapter, that's the way you're going to see hydrogen. Happy with 2. It loves to make single bonds. It can't make double bonds because once you overlap once and get 2, you're done. Hydrogen is only shooting for 2 because it's in the first group. Not boron and nitrogen, though. They love 8, like most of the elements. Let's check out nitrogen first. It donated those 2 in, but it still now gets to count them as a shared pair. 2, 4, 6, 8. Good? Okay. 2, 4, 6, 8. Boron is also happy with 8. Now, what would be the social analogy to this? Well, if you want to get a piece of pizza with your friends, and let's say pizza costs $2, and you have $1, and your friend has $1, right? That's a traditional sharing. You say, hey, let's chip in, and let's get the piece of pizza, and you have a couple of bites, I'll have a couple of bites, and we'll both at least not be completely starving, okay? So you share by each one of you bringing $1. But on another day, if you guys are good friends, somebody might have $2, and the other person doesn't have anything. Well, that's okay too. You could still share because the person who doesn't have any money will just pay the next time. So that's kind of like a coordinate covalent bond. I have $2, you don't have any, but let's still share, right? We can still get a piece of pizza and have a couple of bites each. Okay, that's what good friends would do. All right, perfect place to end, guys. That got us up to page 6 of the notes. I think we're going to be able to get done in just 2 more videos for this chapter. Thanks.